The nature of magnetism. Magnets were first discovered over 2,000 years ago by the Chinese and the Greeks and were used for various non-scientific purposes. The name was coined by the Greeks because certain magnetic rocks, which were later named magnetite, were found in the province of Magnesia, named after Magnesia. And unlike electrical effects, which we've studied in some great detail, which started by rubbing various substances together which would separate the electrical charges so you could see the attractive and repulsive forces, these magnets came out of the ground already and attracting and repelling certain materials. You didn't have to do anything to them. It took another 1,000 years before the Chinese, European, and Persian mariners, those are people who go to sea, separately used magnets for navigation. When you took a magnetic material, shaped it in the form of a little needle, and floated on a surface of water, it always pointed in the same direction, towards the North Pole. Always being able to tell which direction was north is a critical factor in ushering in the age of exploration. You had to know where you were going. And once you know north, then you know south, east, and west. However, it took another 600 years before William Gilbert explained what was going on. But first, let's talk about the nature of magnetism. Magnets have two ends, which we will call poles, called north and south. Like poles repel, so if I have two south poles near each other, they'll repel, or two north poles, they'll repel. Opposite poles attract. What is this analogous to? Well, certainly when we did charges, we found a plus and a minus attracted, and a plus repelled. So very similar here, except in magnetism we call them poles, and this is the magnetic force. When a magnet is cut in half, each piece still has a north and a south pole. No matter how many times the magnet is cut, the pieces still have a north and a south pole. You can never just get a pure north pole or a south pole. This works all the way down to the atomic level. So you can see we have a magnet here, we cut it in half. We now have a north pole here, a south pole here. Then on the other piece of the magnet, we have a north and a south pole. Cut it one more time. The exact same thing happens. We have a north and a south pole, north and a south. Nowhere do you cut this and then you would get one magnet with just the north pole and the other with the south. No, they both have a north and a south pole. So let's compare magnetic poles and electric charges. The behavior of magnetic poles, north and south, are very similar to the electric charges, which are positive and negative. North and south, positive and negative. Now don't think that the north is like the positive and the south is like the negative. These are arbitrary conventions. Opposite poles attract and opposite charges attract. Like poles and like charges repel. However, there are two significant differences between these two types of force. One, certain materials are naturally magnetic, where electrical properties you have to have physical rubbing. They are not naturally electrically charged. And secondly, there are independent positive and negative charges. We did that the last couple chapters. We'd say we had a positive charge here, a negative charge over here. They'd attract each other, but they were two separate entities. However, magnetic materials always have a north and a south pole. You will never find a north pole by itself. Now you have to be careful saying the word never in physics and science. People are still actually looking for something called a magnetic monopole, where you would have just a north pole or a south pole. To this date, it has not been found.